Scientists have identified 121 giant planets which may have habitable moons orbiting them. A report in the Astrophysical Journal identified the planets which could potentially host moons capable of supporting life. The findings will guide the design of future telescopes that can detect these potential moons and then look for telltale biosignatures in their atmospheres. Since the 2009 launch of NASA's planet-hunting Kepler Space Telescope, scientists have discovered more than 2,000 exoplanets, that is, planets beyond our solar system. The primary goal of Kepler was to identify planets orbiting in the habitable zones of their host stars. These are the Goldilocks areas around the star, where it's not too hot and not too cold, but just right for liquid water, essential for life as we know it, to pool on the planet's surface. Terrestrial planets have always been prime targets in the search for life beyond Earth. That's because some of them might be geologically and atmospherically similar to the Earth, the only example of life in the universe we know of. But another place to look are the many gas giants identified during the Kepler mission. While not candidates for life themselves, Jupiter-like giant gas planets in the habitable zones of their host stars could harbour rocky moons called exomoons, and some of these moons may well have conditions capable of sustaining life. There are currently 175 known moons orbiting the 8 planets in our solar system, and some of them, such as Jupiter's ice moon Europa and Saturn's ice moon Enceladus, are thought to contain large liquid water oceans deep under their frozen crusts. So gas giants orbiting other stars could also host large moons, some of which may also contain liquid water oceans. And scientists have speculated that at least some of these exomoons could possibly provide favourable environments for life, perhaps even better environments than Earth. That's because these exomoons would receive energy not just from their host star, but also from the heat reflected from their planet. Until now, very few exomoons have been confirmed. But now that astronomers have created a database of the known giant planets in the habitable zone of their stars, observations of the best candidates for hosting potential exomoons will be made to help refine the expected exomoon properties. One of the study's authors, Michelle Hill from the University of Southern Queensland, says follow-up studies will help inform future telescope design so that astronomers can detect these moons, study their properties, and look for signs of life.
So far, the search for habitable worlds was mainly focused on looking for Earth-like planets in the habitable zone of their star. And the habitable zone is the distance from a star where a world could be, and if there is water on the surface of the planet, it would be in a liquid form. So it wouldn't be too hot, so it's all evaporated off, or too cold, so it's all frozen. And we wanted to look, though, at whether moons could be more prevalent in the habitable zone of their stars. Already, there's been a lot of interest in the moons of our solar system. The moons around Jupiter and Saturn have shown indications of liquid water oceans under their surfaces, and so could potentially be life-holding worlds. So we wanted to extend that to exoplanets and exomoons and see how many of these exomoons could potentially be in the habitable zone of their star. We had to do this by looking at the gas giant planets that the moons would be in orbit around. And so we did a study on how many of these gas giant planets reside in the habitable zone of their star, and how does that occurrence rate compare to Earth-like planets, which has already been studied in great detail.
It must be really hard determining which planets would have moons orbiting them.
Yeah.
Especially considering, from what we now know, it looks like our solar system is the outlier. It doesn't follow the normal practice of other solar systems.
Yeah, so we can do a couple of things. So if we look at our giant planets, Jupiter and Saturn, Jupiter has 69 moons and Saturn has 62, and Neptune and Uranus, even though they're smaller, they have quite a few moons as well. So because of the mass of these planets, they have the ability to sort of hold on to their satellites better than the smaller rocky planets do. And even though the habitable zone is a bit closer in, and so it would be under greater gravitational pull from the star on the planet, we would still expect there to be many moons for these giant planets. So maybe not in the 60s like Jupiter and Saturn because they are further out, but we still expect quite a few moons. And so we looked at the occurrence rates of the giant planets in the habitable zone, and we found that they are slightly less than that for Earth-like planets. But considering we expect then each giant planet to have multiple moons, then we can expect that there is at least as many or even more of these moons in the habitable zone as there are Earth-like planets. And so essentially our study has increased the number of potentially habitable worlds that we can observe out in the universe.
How do you find a moon around an exoplanet? Transit method wouldn't work. What about, are you hoping for some sort of a Doppler shift method to notice the slight change that in orbital velocity that a moon would cause on its host planet compared to the planet orbiting its host star?
Yeah, so the detection method that's going to give us the most fruit, I guess, it hasn't been found yet. There's a lot of different people trying different ways. Transit timing variation seems to be one of the most popular ones, where there's very, very slight variations in the transit of the planet because the moon might be in front of it or behind it. So it's sort of looking at the very edges of when the transit starts to happen and seeing if you can find a signature there. Imaging is a really interesting one. If we can get our telescopes up to a point where probably 100 times better than they are now, then imaging actually could be quite useful because these moons can be quite far away from their planet. So if we get the resolution to a point of about 400 times 10 to the negative 6 arc seconds, then we'll be able to image them. That's probably the two main contenders at the moment. So radio velocity detection or like Doppler detection, I don't think is going to have the kind of precision that we need to find these moons, unfortunately.
I guess the big hope would be at some stage in the future some sort of gravitational microlensing. Planets have been found that way.
Yeah, so actually microlensing is another one that people are trying to use. So, I mean, watch this space.
Indeed. Okay, so where to now? You've crunched the numbers and now we sit back and wait for the technicians to build the telescopes?
I found in the following study 121 of these giant planets that reside in the habitable zone of their star. So these are already known planets. I just gathered them together in a list and ordered them in priority for which would be the best to observe for potentially hosting moons. And so from these 121 planets, the next stage is we're going to observe them with radio velocity detection methods because a lot of them, over 50 of them, showed indications of other planets in orbit with them that haven't yet been detected as well. So we'll be observing the stars to see if we can detect these planets, and then for the whole set we will be observing them to refine the orbital parameters of the planets to help in future exomoon detection. So the reason is because these giant planets are far out from their star if they're residing in the habitable zone, and so their observations of them so far are probably very limited because the orbital period is so long. And so the more detections that we can make of the planets, the better the parameters are refined, and then that will help in future exomoon detection.
These are dreaded three-body systems. Oh dear.
Exactly.
Well, when you talk about planets in habitable zones, what sort of stars are you actually looking at?
We've been focused mainly on stars similar to the Sun, so G and K stars, and also M stars, because these are less volatile and so they're easier to confirm that the planets are there and it's not just activity of the star.
The problem I have with M stars, I guess, is they're sort of a bit excitable and consequently they tend to fry anything on the surface of planets orbiting nearby.
Yeah, exactly. And we also have a problem if we're looking at gas giants. Gas giants around M stars are less common just because of the mass isn't there to build the giant planet. There are a few, but it's just in our study we found that they're
good potential targets, I guess, just to test the hypothesis.
Yeah, exactly.
That's Michelle Hill, an astronomer with the University of Southern Queensland.